Hello, let's begin today's lecture session on multivariate calculus integration. In the last few sessions, we have talked about line integrals and the Green's theorem which relates line integrals with double integrals. Today we will see surface integral. What is that? As the name suggests, a surface integral is an integral where the function to be integrated is evaluated along a surface in three-dimensional space. Say, here we have a surface S in the three-dimensional space and we would like to integrate a function along this surface. Now we may note that this surface integral is the generalization of double integral because we may remember that double integrals are evaluated over a region in the xy plane. That means a plane surface. And now we generalize that concept to integrate along a surface in three-dimensional space. Line integrals we have seen are of two types. Line integrals of scalar fields and vector fields. Here also it's the same. We may have surface integrals of scalar fields or surface integrals of vector fields depending on the function to be integrated is a scalar field or a vector field. In this course, we will see only surface integrals of vector fields. But before we proceed to define surface integrals, first let us see how do we represent a surface. A surface S in Cartesian coordinates may be represented as some function of xyz equal to 0 or z as some function of xy. Say for example, we know that the equation of a sphere is given by x squared plus y squared plus z squared equal to 0. So this is of course in the form f of xyz equal to 0. Now the parametric representation of a surface S is like this, that we have the position vector r of uv given by x uvi plus y uvj plus z uvk, where I, j, k are of course the unit vectors in the x, y, z directions. And the coordinates uv range over some domain d of uv of the uv plane. And the continuous functions u equal to phi t and v equal to psi t of a real parameter t represents a curve on this surface. For example, the circular cylinder x square plus y square equal to a square and z varies from -1 to 1 in parametric coordinates may be represented as r of uv equal to a cos ui plus a sin uj plus vk, where of course u varies from 0 to 2 pi because it's a circle and v varies from -1 to +1. And also note that the curves v equal to constant are actually parallel circles and the curves u equal to constant are vertical straight lines. Next, let us see some more important terms as tangent plane and surface normal. So a tangent plane of a surface S at a point P is the plane containing all the tangent vectors of curves on S through P. Say here, S is the surface in the three-dimensional space. P is a point on S. So this is actually the tangent plane, the plane which contains all the tangent vectors of the curves on S which are passing through P. So here we have shown a curve C1, this is a curve C2 and the tangent vectors are here T1 and T2. And these tangent vectors are comprising this plane of tangents which we call the tangent plane. And now a normal vector of a surface at the point P is a vector perpendicular to the tangent plane of S at P. So here is the normal vector which is perpendicular to this tangent plane. And how can we represent this normal vector? Say that if the surface is represented as f of xyz equal to 0, we know that gradient f or grad f represents a normal vector to the surface. And therefore the unit normal vector may be represented by grad f by mod grad f. And what happens in parametric form? See that when we are representing the surface in parametric form, del r del u and del r del v are the tangent vectors to S at the point P. So the normal vector may be represented as del r del u cross del r del v, and therefore the unit normal vector is given by del r del u cross del r del v divided by modulus of del r del u cross del r del v. Let us see some more basic definitions. A surface S is said to be closed if it is the boundary of a solid region. For example, a sphere is a closed surface, whereas a hemisphere will be an open surface. Next, a surface S is said to be a smooth surface if F has a unique normal at each of its points whose direction depends continuously on the points of S. Next, let us see what is a piecewise smooth surface. So if the surface consists of finitely many smooth portions, it is called piecewise smooth. Lastly, a surface S is said to be orientable or two-sided if the positive normal direction at any point of S can be continued in a unique and continuous way to the entire surface. Now, normally the surfaces we deal with will be orientable surfaces. So let us now proceed to define surface integrals of vector fields. So consider the vector field f of xyz and a surface S defined by the position vector r of uv given by xuvi plus yuvj plus zuvk, where uv belongs to D. We assume that S is a piecewise smooth surface and has a normal vector at every point of it. Then the surface integral of the vector field f over the oriented surface S is defined as f dot ds over the surface S, or more explicitly f dot n ds. What is n? N is of course the unit normal vector. Now see that this integral naturally arises in flow problems where it gives the flux across S. For example, if F is rho v, where rho is the density and v is the velocity vector of the fluid flow, then this surface integral will actually give the mass of fluid crossing S per unit time. And this is why the surface integral is sometimes also called the flux integral, or the flux of the vector field across the surface S. We'll now see one more definition, solenoidal vector. This you may have seen while you learnt multivariable differentiation. Here we define it like this, that a vector point function f is said to be solenoidal in a region if its flux across every closed surface in the region is 0. Now let us see how do we evaluate actually surface integrals. When we are representing the surface in parametric form, we have seen that the unit normal is given by del r del u cross del r del v divided by the magnitude of this expression. And note that the surface element ds will be given by modulus of del r del u cross del r del v du dv, because we know that this mod del r del u cross del r del v actually gives the area of the parallelogram with the sides del r del u and del r del v. So then in parametric form, the surface integral may be represented like this, that f of xyz dot n ds over the surface S is given by now f of x of uv, y of uv, z of uv, and in place of n ds we now put up this value of n and the ds, so it gives us dot del r del u cross del r del v du dv, as this expression in the denominator cancels with this in ds. And we are of course integrating over now the region D in the UV plane. So notice that actually surface integrals are evaluated by converting the integral into a double integral in a plane. Okay, but instead of using the parametric form, a surface integral may also be evaluated by projecting the surface on any of the coordinate planes. like xy or yz or zx planes. So let us see how do the expressions look like now. So first suppose that we are projecting the surface S on the yz plane. So see that the surface element ds is having the projection dy dz in the yz plane. So note that if the normal vector makes an angle alpha with the x-axis, then this dy dz is given by cos alpha ds. And also see that if this unit vector n is actually cos alpha I plus cos beta j plus cos gamma k, then cos alpha is given by nothing but n dot I. And we take a modulus sign to guarantee that we have a positive sign because we are talking about surface elements. And now the surface integral f dot n ds will be given by this expression because now we replace ds by dy dz by n dot I. And we integrate now over the region R, where R is the projection of S on the yz plane. Now similarly, if we project the surface on the xy or zx planes, then we may also write the surface integral in these forms. So if we are projecting on the xy plane, the expression becomes f dot n dx dy divided by mod n dot k. And if we are projecting on the zx plane, it becomes f dot n dz dx by n dot g. We may apply any of these formulas in doing problems. Let us now look into a problem how to evaluate surface integrals. So the question here is evaluate f dot ds over the surface S, where f is yj minus zk and S is the surface given by the paraboloid y equal to x square plus z square, y lies between 0 and 1, and the disk x square plus z square less or equal to 1 at y equal to 1. Assume that S has positive orientation. So let's draw the figure first representing the surface S. Now notice that the surface S actually comprises of two surfaces. One is the surface of the paraboloid and the other is the surface of this unit disk. So here in this figure we have denoted S1 as the surface of the paraboloid y equal to x square plus z square and y extends from 0 to 1. And this S2 represents the unit disk x square plus z square less or equal to 1 located at y equal to 1. So essentially then our S is made up of S1 plus S2, and therefore to evaluate this surface integral we actually have to evaluate two surface integrals, once along S1 and next along S2 and then add it up. So let us first do it for S1 and let f of xyz equal to x square plus z square minus y. So grad f is 2xi minus j plus 2zk. So let's see now how the surface integral looks like. So the surface integral f dot ds over S1 is given by this expression now as f is yj minus zk. And this ds actually stands for unit vector n ds surface element. So the unit vector n is grad f by mod grad f. So we write the expression for grad f over here. And the surface element ds will be now given as mod grad f dA, where dA is a surface element on the projection region which lies on the xz plane, and we denote that with d now. So if we calculate this, this will give us minus y minus 2z square dA over the region D. So let us now proceed to evaluate this double integral over the region S1. So this is this expression minus y minus 2z square dA over D, and we now replace y by its expression x square plus z square. So this becomes minus the double integral x square plus 3z square dA over the region D. And what is D? We see very clearly that the projection of this surface S1 on the xz plane is nothing but this unit disk. So we transform the coordinates into polar coordinates and take x as r cos theta and z as r sin theta. So the double integral now takes this form that the integrand now becomes r square cos square theta plus 3r square sin square theta, and we know very clearly that this surface element will be given by r dr d theta in the polar coordinates. And what are the limits of r and theta? For a circle of radius 1, of course, r varies from 0 to 1 and theta varies from 0 to 2 pi. So we now just evaluate these two integrals, cos square theta plus 3 sin square theta, and now here we have r cubed dr d theta. So r cube, as we integrate, we will get r4 by 4. And in order to integrate this part with respect to theta, we express cos square theta as 1 plus cos 2 theta by 2, and this sin square theta as 1 minus cos 2 theta by 2. After a simplification, this becomes minus 1 by 8, 0 to 2 pi, 4 minus 2 cos 2 theta d theta. So as we integrate, we will get 4 theta minus sin 2 theta, and put the limits from 0 to pi, the answer is going to be minus pi. So we have now evaluated the surface integral over S1. Let us now evaluate the surface integral over S2, which is the circular disk. So we have put here the value of f, yj minus zk, and please note that the normal vector for this S2 is nothing but in the y direction. So the unit normal vector is j. So as we evaluate this expression, it just gives us the double integral y ds over s. Again note that this circular disk is positioned at y equal to 1. So this reduces to just the double integral ds over s2. And S2 being a circle of radius 1, the area of course is pi. So the value of this double integral is now pi. So what is the final answer? The required surface integral f dot ds over s will be given by f dot ds over s1 plus f dot ds over s2. The first integral we have obtained is minus pi and the second one is plus pi. So finally the answer is 0. So with this, we close today's session. In the next lecture session, we will see a very important theorem, that is Gauss's divergence theorem, which will relate the surface integrals with volume integrals. Volume integrals are essentially triple integrals. So thank you and goodbye till then.